Okay, here's another ridiculous physics problem. We have a ball of clay that's traveling east, and it has this velocity, and it collides with another ball of clay that's traveling north. And the question is, what are the speed and direction of the resulting 50-gram ball of clay? So what we can infer from this thing is that these things have stuck together when they collided at some point. So what I would do to solve this problem is I would kind of start out with some sort of diagram where I had north, south, east, and west, and excuse me, I know that I've got some ball of clay that's traveling, let's see, east. It's traveling east. So I'm going to say that here's my ball. It's going this way, east, due east, at 3 meters per second, and this ball happens to be 20 grams. I've got another ball that is traveling north. That would be this direction. And this one is 30 grams, and it's traveling at 2 meters per second. And we are guessing that there's a collision that happens, let's say right here, and it clumps into another ball that magically travels, I don't know, some direction like this. So what's tricky about this one is that of course, you can see that we've got now, kind of a 2D problem. We've got a north and east direction, which means we have to turn to vectors in order to solve it. So what I'm going to do is just remember that I guess I'll do it this way, that we know that the momentum before, the m times v before is going to be equal to the m times v after. Okay, so because the momentum is conserved, or we're going to presume it's conserved. And so what we need to do is say that before we have 20 grams traveling at 3 meters per second, and now I need to take care, I'm going to put grams here, take care to indicate that this is going in the east direction. So if I call this x direction, and I call this the y direction up here, I can use like what's called a unit vector for x, and oftentimes it's indicated with the vector I hat. I can give you x and y, but I'm going to give you I hat plus the vector for y, or the momentum in the y direction, is 30 grams going at 2 meters per second, and the j direction. So this is the unit vector for y will be what we call j, and for x the unit vector is I. And what I'm saying is unit vector. What that means, a unit vector, that's sort of code to mean, unit means 1. So 1 unit in that particular direction is the I. For y, it's the j. Okay, so what I'm saying is that before they collide, the momentum looks like this: 20 grams times 3 meters per second in the x direction, 30 grams times 2 meters per second in the y direction. So that, of course, has to equal the momentum after. Now, the only thing we know about the after is, is that the total mass is 50 grams. So we know that, let me see if I rewrite this, this equals 60. I'm going to drop the units just for a bit. 60 plus 60 j equals 50. We don't know what this is. I'll say 50. We know it's 50 grams times the velocity. I'm going to say v x in the times I plus 50 vy times j. These are meant to be grams. So in just comparing these, you can see that this guy must equal this one. Therefore, since, for example, let's just take the x. We can see that for the x, we have 60I equals 50Vx times I. And if I were to write that separately, I could say 60I equals 50Vx, velocity in the x direction, times I. Of course, the I drops out, and we get this, and we get that 6/5 equals the velocity in the x direction, or the component of velocity in the x direction. Now, notice that the numbers for y are the same. So what I know if I were to do it this way, I know that Vy would also be equal to 6/5. So what I know is that my final velocities from this equation is, or my final momentum from this equation is equal to this. Basically, it's equal to this. And we know that Vx is equal to 6/5, equals 6/5, or 1.2 meters per second for Vx and Vy. Now they're asking what are the speed and direction of the resulting 50-gram ball. Well, we know now that the velocity final looks like this. It looks like this. It looks like 1.2 I plus 1.2 J meters per second. So in order to get the magnitude of this final velocity, what we have to do is figure out what the magnitude of this vector is. So you can see it has an x and a y component. So the velocity, the actual value of the final, is equal to the square root. Just like this is a triangle, we know that the x component of this is going to be 1.2, and I know this is not to scale, 1.2 meters per second. The y component is 1.2 meters per second. I didn't write this in the right place. 1.2 meters per second. Oh yeah, it's kind of messy here. Let me do it in red. So we got 1.2 meters per second. This is not to scale. And then we've got 1.2 meters per second in this direction. And then, so the value of the velocity is this, the hypotenuse of this triangle. So to find that, we just take 1.2 squared plus 1.2 squared, and that equals the square root of the sum of those, and that is equal to, what is that, 1.2 squared, that's going to be 0.144 plus 0.144, is that right? 12 squared. I think that's right. Times 1.2 times 1.2. Oh no, 1.44 plus 1.44. The square root of that. That's about 2.88. What is the square root of 2.88? Does anybody know? Is about equal to I'm going to call that 1.6 meters per second. And I'm going to pause this to use a calculator to check it. Okay, it's actually 1.7. I checked this, it's 1.7 meters per second. Using a calculator, it was close. Okay, what are the speed and direction? So the direction is, they are colliding. This, you can see this is the northeast direction, and the speed is 1.7 meters per second, or one significant figure, 2 meters per second.